Hello, I'm Yang P. Liu, and today I'm going to be presenting on a Gaussian fixed point random walk. This is joint work with Ashwin Sah and Mehtaab Sawhney, who are at MIT. The key notion that we're going to be concerned with in this talk is the problem of online vector balancing. In this problem, there's vectors v1 through vt in n dimensions, which arrive one at a time. When a vector arrives, we want to assign it a sign, which is either plus or minus 1, and maintain a small discrepancy. In other words, we wish to keep the quantity max over all times of the L infinity norm of the signed partial sum up to times t small. Online vector balancing or vector balancing has numerous applications to various fields of TCS, including balancing covariates in randomized controlled trials or online NV minimization algorithms. In general, algorithmic discrepancy has been an active field since works of Bansal and Lovett-Mecca gave a polynomial time algorithm to construct solutions to Spencer's 6 standard deviation suffice. To get a feel for the online vector balancing problem, I just wanted to give an example. So, for example, in the first step of an online vector balancing instance, maybe the vector arrives minus 1, 1, 1, minus 1, and we'll assign it a sign of 1. And then we compute the partial sum. Then the next vector arrives and we assign it a sign, and we compute the partial sum, and we keep going in this way. And our goal would be to make sure that every partial sum doesn't have a very large L infinity norm. The specific setting that we focus on in this talk is called the Komlós setting. In the Komlós setting, all the vectors have L2 norm of most 1, and we assume an oblivious adversary. The vectors v1 through vt are all fixed beforehand, and they don't change depending on the randomness used in our algorithm. This is a natural setting because the oblivious adversary model actually generalizes the offline model, where all the vectors are given to the algorithm up front, and we can look at all of them and decide all the signs at the same time. Additionally, the stronger model of adaptive adversaries admits a square root t lower bound, because what the adversary can do is pick the next vector adaptively depending on the previous vector. In particular, it'll pick the next vector to be orthogonal to the previous partial sum maintained up to that point. Thus, the length will grow by 1 every step, and it'll lead to a square root t lower bound. To describe the previous known results for vector balancing in the Komlós setting, it's useful to introduce the Komlós conjecture. This conjecture asks whether given vectors v1 through vt in n dimensions, all with L2 norm of most 1, that there must be signs epsilon 1 through epsilon t such that the L infinity norm of the signed sum is bounded by some constant. An even stronger conjecture, the Komlós conjecture for prefixes, as I'm going to call it, asks whether given vectors with L2 norm of most 1, the same setting of the Komlós conjecture, that there's signs epsilon 1 through epsilon t that are plus minus 1, such that all signed partial sums for all the prefixes also are all at most O of 1. So it's not known whether either of these conjectures is true or false. The best known results towards these conjectures are the best upper bound of O of square root log t, which works for all prefixes. This is due to Banachik. Additionally, it's known how to give a polynomial time algorithm that achieves a square root log t bound for the total sum. So like not all prefixes, but just the total sum of the Komlós conjecture setting. And additionally, there's an online bound in the Komlós setting that achieves an O of log t discrepancy that also works for all prefixes. And this is work of Allweiss, myself, and Sawhney. So as you can see, there's still a gap between the best upper bounds and lower bounds for the Komlós conjecture and the Komlós conjecture for all the prefixes. In particular, it's not known whether there's an online algorithm that can achieve a square root log t bound for all prefixes. And in fact, it's not even known whether there's a polynomial time algorithm that can achieve a square root log t bound for all prefixes. Towards this, here are our results. So we show that in the Komlós setting that there's an online algorithm that works against oblivious adversaries and selects signs that are either plus minus 1 or 0, but a small fraction, 4% of the signs at most, are 0. And the discrepancy is O of root log t on all prefixes with high probability. Additionally, we also show that in the Komlós setting that there's an online algorithm against oblivious adversaries that selects signs epsilon I that are either -1, 1, or 2 that achieves discrepancy O of root log t with high probability, once again for all prefixes. Additionally, both these algorithms described will run in nearly linear time in the input. So the first result on partial colorings recovers an O of log t bound for online discrepancy with only -1, 1 sign. This is because you can recolor online the signs that are colored 0, and it will terminate in log n rounds, and you can use some concentration bound. However, these results still do fall short of matching Banashik's O of root log t bound online because of these additional 0 or 2 signs that we're allowing in these theorems. However, maybe these theorems at least make me optimistic that a O of root log t online and prefix discrepancy algorithm that only uses -1, 1 colors is achievable. And maybe just towards this intuition, somehow it seems like as long as you add any little bit of power to the -1, 1 signing, such as a very small fraction of 0, or this like 2 signing, then you can achieve this goal of O of root log t. So at least I'm very optimistic that an O of root log t bound with only +/-1 signings should be doable, but we're just missing some tools to do it at this moment. Now I'm going to describe our main algorithm for proving this theorem. So the first part is that we give this thing called which we call a Gaussian fixed point walk. The precise statement of that is, we show that there is a Markov chain on R, so one-dimensional, and the steps are signed either -1, 0, 1 or -1, 1, 2, and at most 4% of the steps are going to be 0, and the stationary distribution of this Markov chain is exactly the normal distribution with mean 0 and variance 1. To use this theorem to give a discrepancy algorithm, here's what we do. For simplicity, let's consider the case where all the input vectors have L2 norm 1. We're going to initialize a starting vector, W0, to be normally distributed in n dimensions. When the vector vi arrives for I from 1 to capital T, we're going to first imagine decomposing the n-dimensional normal distribution into one-dimensional normal distributions or Gaussians in the direction of the input vi. Now we're going to imagine, let's take our partial sum wi and imagine which of these normal distributions it's on. We're going to take one step of the Gaussian fixed point walk described, and then we're going to get the sign epsilon I from the Gaussian fixed point walk and add it to our partial sum wi minus 1. So basically, just to describe it again, we're going to decompose the n-dimensional normal distribution into one-dimensional slices and then simulate the Gaussian fixed point walk on one of those slices, depending on where our current partial sum lands on them. To understand why this algorithm works, the main claim is that by induction and the stationary distribution guarantee of the Gaussian fixed point walk, the distribution of the partial sum wi will be exactly n0i, the normal distribution in n dimensions, every step. Thus, for any partial sum, I from 1 to little t, of epsilon I vi, it's going to be the difference of two which are coupled Gaussians with distribution n0i. This is because the wi has distribution n0i, and the initial random vector w0 that we picked also distribution n0i. So this partial sum is distributed as the difference. Hence, with high probability, the L infinity norm of the partial sum is going to be O of root log t with high probability. Thus, it suffices to understand how to actually build this Gaussian fixed point walk. That's going to be the focus of the remainder of the talk. So just to remind everyone of the goal is to build a Markov chain in one dimension whose stationary distribution is n01, and the steps are either -1, 0, 1 with a very small fraction of zeros, or -1, 2. So notice that because all our steps are integers, we can actually treat the one-dimensional, well, the real Gaussian as the union of a bunch of discrete Gaussians. In particular, you can treat the points f plus z separately for any fractional part f in -1/2 to 1/2. For the purposes of the remainder of the talk, we're going to focus on the case f equals 0. And our goal is just going to be to build a Markov chain on z now, whose stationary distribution is proportional to x of minus x squared over 2. So basically proportional to the discrete Gaussian on the integers. Towards building this Markov chain on the discrete Gaussian, it's actually useful to understand first why no such Markov chain exists whose steps are size -1, 1. So in particular, you actually need to allow a small fraction of zeros or like an extra 2 signing, or else it's actually not constructible. We call this the parity constraint because of the following. So let's say that such a Markov chain existed. Then notice that because the steps are size -1, 1, that every step must go from an even number to an odd number or vice versa. Thus, if the discrete Gaussian on Z is the stationary distribution, the total even mass and the total odd mass must be equal. However, you can directly check numerically that the sum of even x's of x of minus x squared over 2, the discrete Gaussian mass, is not equal to the sum of the odd mass. So therefore, there is no Markov chain with steps -1, 1, whose stationary distribution is proportional to x of minus x squared over 2. So once we've made this observation, you can actually construct the walk in a fairly direct way, given this extra power of allowing a small fraction of 0 signs or 2 signs. So more precisely, to construct the walk, we're going to define the following transition probabilities: mx, which is like the moving probabilities when you're at x, and s, which is a staying probability. It turns out that in our walk on z, the only point which ever will output a sign of 0 is going to be x equals 0. No other points we're going to allow them to stay at the same point. So in that case, the total probability that x equals 0 will stay at the same place should actually just be the difference between the even mass and the odd mass. And that's exactly what the staying probability s is. It's the alternating sum of the even mass and the odd mass. So now, given these transition probabilities, we can just define the following walk. For x at least 1, we're going to move +1 with probability mx and -1 with probability 1 minus mx. So for any positive integer, you either move right or you move left with some given probabilities. You never stay put. For negative integers, you do something similar. You move +1 with probability 1 minus m of negative x and -1 with probability m of minus x. And finally, for x equals 0, you move +1 probability m0, -1 with also a probability m0 symmetrically, and you stay now with probability s. So as you can see, only x equals 0 will stay put or output a sign of 0 with positive probability. So in fact, you can prove that out of walks where only x equals 0 stays put or outputs a sign of 0, that such transition probabilities are actually unique. In particular, as I was explaining, you can derive s exactly as the difference between the even mass and the odd mass because only x equals 0 stays put. And then from there, you could compute these mx's by just like propagating outwards and solving some equations. So these are actually uniquely defined, and you can kind of just solve for them algebraically. So given these transition probabilities mx and s, you can kind of directly check that the discrete Gaussian on Z is the fixed is a stationary distribution for the walk. There is one piece that needs checking though, just to formally show that the walk is well defined. You have to show that M is actually between 0 and 1, and that S is also between 0 and 1. While, as stated, this can basically be checked numerically, there's other instances in our paper where you need a more fine control on what M and S are, and I want to explain an alternate method to understand why, for example, the staying probability S is between 0 and 1. So first, you could just numerically compute S and check that it's between 0 and 1. In particular, S is less than something like 3.7%. And this is where our claim that at most 4% of signs are 0 comes from. An alternate way to bound S or to compute the value of S can be via the Jacobi triple product formula. This very beautiful formula says that for complex numbers U and V, we have that the sum over all J of U to the J squared, V to the 2J, is given by some triple product. We can apply this to express the formula for S in an alternate way by taking U equals X to the minus 1/2, V is root minus 1 in the Jacobi triple product formula to get that S is in fact the product of the following quantities as written. So notice that all the quantities in the product are between 0 and 1, and in fact, you can show that it converges. So evidently, we get that S is strictly between 0 and 1. This ends up being useful in our paper because we also analyze instances where we want the stationary distribution to be N0 sigma for some variance sigma larger than 1. And the Jacobi triple product formula actually gives us tighter control on what the probability is that the walk stays at 0. So now I just wanted to conclude with some comparisons to other works. The work of Allweiss, Liu, and Sawhney gave an algorithm for online discrepancy. Their algorithm and analysis were based on proving that the distribution of the partial sums, Wi, were spread by some normal distribution with covariance O of log t times I. In some sense, you can view this Gaussian fixed point walk as a limit of this. So their algorithm argued that the distribution maintained was smaller than a Gaussian in some sense, while our algorithm just directly maintains that the distribution of the partial sum is exactly a Gaussian. Also, later work of Chewy, Gerber, Rigolet, and Turner built a walk in 2 dimensions instead of 1 dimensions, with steps of length 1 vectors whose stationary distribution was exactly the 2-dimensional Gaussian. Using this, they were able to give an online discrepancy algorithm where instead of having plus minus 1 signings, they had vector signings with 2-dimensional vectors, and they achieved some bounds on the discrepancy in that setting. Given our work, there's several natural future directions to explore. Towards open problems, some natural open problems are to ask whether you can achieve an O of root log t discrepancy bound with signs -1 or 1, or we can ask the easier problem of giving just some polynomial time algorithm that achieves a root log t discrepancy for all prefixes. Additionally, what are any other applications of this Gaussian fixed point walk? And that's the end of my talk, and you can find the paper at the following link. Thank you for your attention.